Okay, so this is a continuation of section 5.2 on Fermat's little theorem. The objectives of this lecture, we're going to give another proof given by Euler. As you know, Fermat actually, when he stated the theorem, all right, he did not actually provide a proof for it. The proof was given by Euler, so we're going to look at Euler's proof for Fermat's, theorem. Euler actually gave it a generalization of Fermat's theorem that we're going to look at in chapter 7. Then we're going to look at how we can use actually Fermat's theorem as a compositeness test for integers. In other words, to show that an integer is composite, we can use Fermat's theorem without knowing any of the, the integers fact. Okay. Then we're going to look at the converse. Is the converse of Fermat theorem, is it true or not? Then we're going to look at special types of primes. Well, they are not primes actually, they are called pseudoprimes and Carmichael numbers. And this one is, of course, we will see the relationship between the converse of Fermat's theorem and these types of numbers. All right, so let's get started on the proof of Fermat's theorem by that Euler gave, and he used the binomial theorem, basically. All right, here is the theorem, all right? Now let be a prime, and A is any integer, then A to the P is congruent to A mod P. Remember, there are two actually formulation of Fermat's theorem. One, when A is relatively prime to B, then we can say that A to the P minus 1 is congruent to 1 mod P. And another one, which is true for any integer A. All right, here's the proof. And this is Euler's proof. Yeah, we're going to do this is by math induction on A. So we're going to take two cases so we can apply the math induction. Case 1, where A is either, it's a non-negative basically integer, either positive or 0. So this is by math induction on A. So if A is equal to 0, then 0 to the P is congruent to 0 mod P, because it's actually equal to 0, so it is congruent. Also for if A is equal 1, the statement is true. 1 to the P is equal to 1, so it is congruent to 1 mod P. So both statements hold for 0 and 1. So let's assume that the statement is true for an integer or a non-negative integer, A. So here's the induction hypothesis. Assume that A to the P is congruent to A mod P for some A bigger than or equal to 0. All right. Now let's consider the statement for A plus 1. So we're going to consider a plus 1 to the p. All right, so we're going to use the binomial theorem. And this one is equal a to the p plus p1. Actually, this is supposed to be p0, which is equal 1. This is a p minus 1, p2, a p minus 2, and so on. And the general term in here is pk, a p minus k, and the term before last is p minus 1, a plus 1. Now let's look at the binomial coefficient, where pk is equal p factorial, then we have k factorial, then p minus k factorial. All right, let's simplify this and write the p factorial as p minus 1, p minus 2, up to p minus k plus 1. And then the next one is going to be p minus k, and then continue, so we're going to put factorial. In the denominator, we have k factorial, then we have p minus k factorial. So we can cancel out the p minus k factorial, and we end up with this expression. I hope it's actually simpler, but we're going to need this for our next step over k factorial. All right, I'm going to look at actually the product. We have k factorial times pk. This is equal to p minus 1 up to p minus k plus 1. All right, I claim that p k here is going to be congruent to 0 mod p for all the k's between 1 and p minus 1. Okay, so we're going to write this claim down. So here's the claim. P k is congruent to 0 mod p. Okay. Really, this is equivalent to saying that p divides, okay, pk for every k between 1 and p minus 1. Okay, so let's see this. Well, as you see in here, from this equation, we know that p, so this implies p divides k factorial and pk. All right, because this is a multiple of p. Now, since p is a prime, this implies p divides k factorial or p divides pk. All right, I'm going to show that the first possibility is it can't happen. All right. Now, since remember this is for every, we wanted to for every k between 1 and p minus 1. And actually, let me start with this. For every k between 1 and p minus 1, the k factorial, all right, cannot have p as 1 of its factors in the product, which is 1 times 2 up to k. All right? So in other words, this means that P cannot divide k factorial because P is a prime and it's going to be any one of those numbers. And this implies P does not divide k factorial. All right, so therefore, P divides Pk. All right, and this is true again for every k between 1 and P minus 1. Now, let's go back at the binomial expansion. So in the binomial expansion for a plus 1 to the p, remember this is equal to 1 plus p1, a to the p, p2, a p minus 2, this make minus 1, and so on. P minus 1, a plus 1. Now, each one of these is congruent to 0 mod p. So this is congruent to 0 mod p. This is congruent to 0 mod p. And this one is congruent to 0 mod p. So in other words, all together we have the a plus 1 to the p is congruent to, actually this is a to the p, a to the p plus 1. All right, mod p. Now, by induction hypothesis, we have a to the p is congruent to a mod p. So if I go ahead and put for this a to the p, so this, if I replace this is by a plus 1 mod p. And this means that the statement is true for a plus 1. Is true for a plus 1. And by math induction, statement is true for every statement for every a in z plus union z. All right, so we proved it for the non-negative integers. Now let's consider it for the negative integers. So let's assume that A is in Z minus. Well, this implies negative A is going to be in Z plus. Then by the first part, we have negative A to the P is congruent to A mod P. if P is equal to 2, the prime 2. If P is equal to 2, this statement becomes minus A squared is congruent to A mod P. Sorry, this is minus A, not A, minus A. Okay? This is minus A. All right. But minus A squared is going to be A squared is congruent to minus A mod 2. All right, this is mod 2. But minus A also is congruent to A mod 2, since minus A is equal negative 2A, and 2 is divisible by negative 2A. All right? So in other words, the statement actually does hold that A squared, where the A is in fact is negative, is congruent to A, where A is negative. Now, if P does not equal to 2, this implies P is an odd, and in this case, minus A to the P is congruent to minus A by what we have shown in the first case. But a negative A to the P is equal actually negative A to the P, congruent to negative A mod P. And I can multiply by negative 1, because negative 1 is congruent to negative 1 mod P. So by properties of congruences, this implies that A to the P is congruent to A mod P. Okay? So you obtain this by multiplying this congruence by negative 1. Or negative 1 is congruent to negative 1 mod P. All right, so this takes care actually of the proof using the binomial theory. All right, now our next objective is to use Fermat's theorem as a compositeness test. All right. You write this down. Fermat's theorem as a compositeness we're going to actually state the contrapositive of Fermat's theorem, which is logically equivalent to Fermat's theorem itself. Contrapositive of Fermat's theorem. All right. Remember what Fermat's theorem, it says that if P is a prime, then for every integer A to the P is congruent to A mod N, mod P, mod P. So the contrapositive is going to say that if A to the P, or let me say actually for an integer, let n be a positive integer such that A to the n is not congruent to A mod n for some A, for some integer A, then A is not a prime. All right? Remember, this is the contrapositive. If I have a theorem which says we have a proposition that is of this form, a statement B implies a statement Q. The contrapositive statement goes like this. The negation of a Q implies negation of P. So in Fermat's theorem, it says that for every integer A, when P is a prime, then we have A to the P is congruent to A mod P. So, so the conclusion is that the Q is actually the congruence. See, if this is not satisfied, then we have the P, which is the statement P, which is P is a prime. Okay? So A is not composite. This is equivalent to say that A another prime is composite. And since the theorem and its contrapositive, they are equivalent, so this is a true statement. All right? Now, what does this mean? This means that in order to show that an integer n is composite, all what you have to do is to come up with an integer a and do the a to the n. If it's not congruent to a, then n is actually composite. Well, if it is, this means that there is a possibility that n is a prime. And what you could do, you could change the a. Means you want to try another a and see if actually the statement actually is not satisfied, or the congruence is not satisfied. In fact, if you try this for small numbers, a, like 2, 3, 5, just need to prime here, and every time you find that a to the n is congruent to a on n for all these different a, there is a very, very high probability that actually n is composite. We're going to be talking about the converse, means actually, and it turns out to be not true, means it is possible for some composite number actually to satisfy this congruence relation. All right? These are what we call pseudo-primes. Okay? So we're going to be talking about this shortly. So let's see, as you can see, in here what we are not saying anything about the prime factors or any factors of n. Okay? It's just simply actually checking it through a congruence relation not being satisfied. And even if n is very large, remember calculating a to the n mod n is simple, is easy by using fast exponentiation, or we call it successive squaring, okay, and then reducing mod n. All right, so let's look at an example how we can show a simple number like 63, in fact, is composite, which we know it is. But we're going to prove this without knowing or without using the factors 7 and 9, for example. All right, so here it is. Okay, so here's an example. That n equals 63, which I know this is 7 times 9. So this is composite, we know that. I'm going to show that actually Fermat's congruence is not going to be satisfied for this. So I'm going to let A equal to 2. Actually, I will start with 2. If it doesn't work, then I'm going to go to 3. But we're going to see that actually 2 does work. And we're going to do this calculation like this. 2 to the 63. I want to show that this is congruent to actually 2 mod 63. So we're going to see that this one is 2 to the 60 multiplied by 2 to the third, which is 2 to the 10 to the 6 times 2 to the 10. All right, now let's look at, actually I want to do this one, let me do it the other way around. Let me do it the 10 inside and the 6 inside, sorry. So I'm going to do this one, 2 to the 6 to the 10 and 2 to the third. And 2 to the 6 is having actually 64 to the 10 and then 2 to the 10. Now let's consider as 64 is congruent to 1 mod 63. Because if you subtract 1 from the 64, you get 63 divisible by 63. This means that when I take this is to the 10th exponent, this becomes congruent to 1 to the 10th exponent, 63. So now we can go in here to this equation and say this is congruent to 1 times 2 to the third, and which is equal to, of course, 8 mod 60. And of course, this means that 2 to the 63 is not congruent to 2 mod 63, because it's congruent to 8. So by Fermat theorem, actually the contrapositive Fermat theorem, therefore 63 is composite. But the purpose of this exercise is not to discover something new. We know that 63 is composite. It's just to show you that when n is very, very large, all right, and you don't know whether it is composite or it's a prime, then if you use Fermat's theorem and you end up with again, a equal to or 3 or 5, okay, and if you find that one of these congruencies actually is not congruent to the number that you're taking, the a you're taking, then you have shown that the number is composite without knowing any of its factors. All right? So this is the significance of this. However, if you find that all these congruencies are satisfied, there is a very high possibility that the number you are testing is a prime. Okay? However, there is a catch, means unfortunately, because it turns out that there are some composite numbers that satisfy the congruence without being primes in their composite. And actually, this is what we're going to be looking at next. All right, is the following. Okay, here's the question. Is the converse of Fermat's theorem true? All right, let's look at what is the converse. We go to the side in here again. If you have a statement P implies Q, the converse of this is Q implies P. All right? So we know what Fermat's theorem is saying that if P is a prime, A in Z, then for every A in Z, we have A to the P is congruent to A mod P, right? So the strict converse of Fermat's theorem is this. It's going to be if for every A in Z, all right, A to the power B is equivalent to A mod B, then B is a prime. All right? It turns out this statement is not true. So this is not true. In other words, there are composite numbers such that composite number, let me say A, N, or number N, such that A to the N is congruent to A mod N for every A in Z means the statement is whole. Such numbers are called Carmichael numbers. Now we're going to give them another name, and we're going to define this, formally. But this is just kind of a discussion. And these numbers are discovered by Robert Carmichael in 1912. And actually, conjecture that there are infinitely many of these types of numbers. The smallest of these happens to be 561, in which we're going to see and show that actually satisfy this congruence relation for every A. But the conjecture that Carmichael actually stated in 1912, it wasn't settled, means proved, until 1994, okay, by Carl Hamrens and others, okay, and that was a breakthrough in some sense, and it's an unfortunate thing because if actually Fermat's theorem, its converse is true, it would provide a very simple primality testing. But since it is not, means there are some composite that actually satisfy this congruence without being prime, so we can't use it as the primality test. All right, now we're going to look at even a weaker converse. So, okay, a weaker converse. Let me see here. Means even we don't want it for all integers, A. So here is a we converse are there composite numbers and such that a to the n is congruent to a mod n for some a, for some integer a. And the answer is yes. In other words, we are not insisting for every integer a, but only for some integers, okay, or at least one. Again, such numbers are called pseudoprimes to the base a. All right, so actually let's put the formal definition down, and then we look at an example. All right. Here is how we formally define a pseudoprime to a certain base. Here is the definition. Let B be a positive integer a composite integer n, so it must be composite, okay, integer n is called a pseudoprime or sometimes called fake prime, if you want. It's called a pseudoprime to the base p if b to the n is congruent to b mod n. In other words, it passes the Fermat's, all right, congruence, but it's being composite, so we call such numbers pseudoprime to the base. So let's look at an example. N equal 341, and this is equal to 11 multiplied by 31, so this is composite. So I claim that N is a pseudo prime to the base 2, but it is not a pseudo prime to the base 3, and many others as well. Okay, but I will show it for 3. So in other words, if we want to use a Fermat compositionist test and pick 2, then we're going to see that the congruence actually does hold, which make, initially to say that the 3, 4 to 1, maybe it's a prime. So we pick another A. So if I pick a 3, and we're going to find, no, the congruence doesn't hold, so it must be composite. So this is kind of the idea that how Fermat's actually little theorem is used also for primality testing, except it is not what we call a definite, primality test. It is a probabilistic, means there is a chance that we could be wrong. But it's a very, very high probability that when you apply Fermat's, little theorems for different bases, and every time the congruence actually is satisfied, means this number we are testing most likely is a prime. Okay, unless, of course, one of the unfortunate situation where the number that we are testing, it's a Carmichael number, and there are actually infinitely many of those. But they are very, very, very rare. In other words, their appearance among the numbers is sparse, way far away from each other. All right, so let's go ahead and actually show this. There are several ways we can do this. One is just kind of the more or less brute force using, fast exponentiation. You could do that. Means express the exponent 3, 4 to 1 as sums of powers of 2 and do the squaring, which is not that hard and it doesn't take very long. Or you could use combination of some tricks, and Fermat theorem to do the job. So this is what we wanted to show, or I claim actually 2 to the 340 is congruent to actually 1 mod so I wanted to show, in other words, the other formulation of Fermat's theorem. Remember that we have A to the B is congruent to A mod B. Or if A is relatively prime to B, then we can say this. B minus 1 is congruent to 1 mod B. So I'm going to choose the second one because 3, 4 to 1 is relatively prime, of course, to 2. It's not an even number. So we're going to show this. 3, 4 to 1. All right, to do this, we're going to start with, by Fermat's theorem, we have 2 to the 10 is congruent to 1 mod 11. Okay? Now remember, we also know ahead of time that the 3, 4 to 1 is equal to 11 multiplied by 31. So we know that we're going to need this 11. Then I can say 2 to the 340 is actually 2 to the 10 to the power 34. And this one is going to be congruent to 1 to the power of 34 mod 11, which of course give us 2, 340 is congruent to 1 mod 11. All right, so this is 1. And now let's look at the, for the 31. For 31, to start with, we have 32, which is equal 2 to the 5th, and this is congruent to 1, my 31, right? And now we can write the 2 to 340 is equal 2 to the 5th to the power 68. But 2 to the 5th is congruent to 1, 131, so this becomes 1 to the power 68 mod 31. And this gives us this congruence, mod 31. So we have now 2 to the 3rd, 2 to the power of 340. So we have 2, 340 is congruent to 1 mod 11, and 2, 340 is congruent to 1 mod 31. One other thing we know about 11 and 31, they are relatively prime, and the greatest common divisor of 11, 31 is equal to 1. Then we have this 340 is congruent to 1 mod their greatest common, actually supposed to be in general their least common multiple, but since the greatest common divisor is equal to 1, so this just give us a product of 11 and 31, which is of course 341. This is actually, we proved this when we were talking about the Chinese remainder theorem, okay, some properties that we needed to prove the Chinese remainder. All right, we're going to look at, actually there's another proof we could present using a lemma that is useful for doing such calculations. The next thing I want to, therefore, we have the conclusion that we get out of these calculations that 341 is a pseudoprime prime to base 2. But I say it's not pseudoprime to base 3. So let's consider a 3 to the power of 340. Okay. And I'm going to show this one is not going to be congruent to 1 mod 341. One way to do this is, again, to use brutal force to express this as in base 2, or write it as a sum of powers of 2, and then this is 2 squared. All right, then you can take the 340 is equal to 3 2 to the 8 times 3 2 to the 6 times 3 to 2 squared. And by doing repeated squaring and reducing mod 30, so you're going to 341, you're going to see this is actually congruent to, all right, 245, then 81, then 245, then 81. So each one of these, by doing the powers, let me see it here, 1, 2, 3 in here. At the end, I think, in other words, you could do that, and and you're going to see this is congruent to 56 mod to 341. So this implies that 341 is not a pseudoprime to the base 3. At the same time, actually, this calculation, this shows also, these calculations show 341 is composite. And we didn't use any factoring in here. We just used actually the fast exponentiation, and that's what we have. All right. The next thing I wanted to look at is actually a lemma that is useful in doing or proving some numbers are pseudo prime. All right, here it is. So this is a lemma. Let P and the Q be distinct primes. And assume that we have A to the B is congruent to A mod Q, and A to the Q is congruent to A mod P, where A is a positive integer. All right? Then the conclusion is A to the PQ is congruent to A mod PQ. Now remember that the powers on the A and the modulus are the opposite to each other. This is P, this is a Q, and other words. Okay, let's look at the proof here. We're going to apply Fermat's theorem as follows. So we're going to take A to the Q to the B. So in other words, A to the Q, I want to take it my A, sort of. Okay, so this is congruent to A to the Q mod P. All right. So this one gives me, of course, A to the power PQ is congruent to A to the Q mod P. But A to the Q, all right, is congruent to A mod P. So this one is congruent to A mod P. All right, so we have that A to the power PQ is congruent to A mod P. Now we're going to also similarly if I apply Fermat's theorem as A to the P to the Q, this is going to be A to the B mod Q. But A to the P mod Q is congruent to A mod Q. Now these two congruences imply, just like we did with the previous example, So we have a to the pq is congruent to a mod b, and the same thing is congruent to a mod bq. Then the conclusion we have is a bq is congruent to a mod bq. Again, by a property of, if we have the same congruences for two different primes, for two different, actually even doesn't have to be a prime, as far as the two numbers in here are relatively prime or co-prime to each other, then this statement actually does hold. All right. Actually, with this, we can do another proof for the 341. We can use this lemma to do that. It is it satisfies Fermat's congruence. So I'm going to leave that for you. And I want to move on to proof. Actually, there are infinitely many pseudo-primes to the base 2. Okay? In fact, there are infinitely many pseudo-primes to any base, but we don't want to go very far on this. So the next thing is I want to actually generate, given a pseudo-prime, I can generate another bigger pseudo-prime. So this is that theorem 5.2. Read this way: if n is an odd composite, actually an odd pseudo-prime. So I want it to be pseudo-prime. It's going to be composite, but also satisfy to the base 2. It does satisfy Fermat's congruence. Then m sub n, which is equal to 2 to the n minus 1, is a larger pseudo-prime to the base 2. All right, here's the proof. Two things I have to show. I have to show that m sub n is in fact is composite, and also it satisfies Fermat's congruence. All right. So first of all, we have, since n is a pseudo-prime, n is composite, and this implies that n is equal Rs for some integers R and S with 1 less than R, S less than N. So R and S is not going to equal 1 or N. So these are proper factors of N. All right. Now let's consider this M sub N. So this is equal 2 to the power rs, because that's what n is, minus 1. And I want to write this as 2 to the power r to the power s minus 1. I want to use an algebraic identity that is very simple and easy to prove by either math induction, or you could just multiply it out. And so I want to use this fact. X, if you take it to the nth power, whatever n is, okay, minus 1, this is equal x minus 1. Then we have x n minus 1 plus x n minus 2, and so on. Actually up to 1 plus x plus 1. All right? So in here I'm going to be using my 2 to the power. So we're going to let x equal 2 to the power r in this expansion. So this becomes, all right, 2 to the r to the s, okay? And the n is s in here. So this is going to be 2 to the r minus 1, then 2 to the r to the power s minus 1, then plus 2 to the power r s minus 2, and so on. 2 to the power r plus 1. All right, so this is what it's equal to. Now, we know that neither one of these factors is going to equal to 1, so this one is bigger than actually 1, and the same thing in here. This is bigger than 1. And which makes that actually and remember this one I'm sorry, we need, this one is minus 1. Okay, let me write this, okay? So we're going to let x equal 2 to the r in this mn, okay, which is 2 to the r s minus 1, like this, okay? So we're going to use that formula to express this. So this implies that m sub n is composite. The next thing I want to show 2 to the power m to the power m to sub n minus 1 is congruent to 1 mod m sub n. Okay, to show it actually passes Fermat's congruence. All right. And to do this, again, we're going to be using a similar trick to this expansion. But let's have some room here. All right, first of all, to start with, we have 2 to the n. This is going to 2 mod n, because n is a pseudoprime to base 2. And this implies that n divides 2 to the n minus 2. And this makes 2 to the n minus 2 is equal n to q for some q in z, or some integer q. All right, let's look at now 2 to the m sub n minus 2, which we can factor a 2 out, and then we have 2 m sub n minus 1, all right? And gonna work on this 2 to the power m sub n minus 1. Okay, so we're gonna consider this. Okay, so 2. Well, the m sub n is, remember, this is equal to 2 to the n minus 1, all right, and then also minus 1. Okay, so this is the m sub n, all right. So altogether, this is going to be 2 to the power n minus 2. But 2 to the power n minus 2, this is actually n cubed. So this is equal n cubed. So we're going to substitute this one here. And now we're going to go back to this 2 to the m sub n minus 2 is equal to, and then 2 to the n cubed minus 1. And again, I want to use the expansion, that xn minus 1, and to this one. So I want to write this is 2. And let me write it as actually 2 to the n to the power q minus 1. And let's expand. So this one is 2 to the power n minus 1. Then 2 to the power n q minus 1, and plus 2 to the power n q minus 2, and so till the plus 1. All right, now we need to take this mod m sub n, all right? So again, that one is equal to this, and let's see what this is equal to. All right, let me write it down in here. So we have, this is what we have, sub n minus 2. We have shown this is equal to 2 and 2 to the n minus 1 multiplied by all this other stuff there, which is 2 to the n q minus 1, 2 n q minus 2, and so on plus 1. All right, so this is equal to 2. This actually is equal m sub n with all of this. But since it's a multiple of this means this is congruent to 0 mod m sub n. And this is it. So we have this one is congruent to 0, means 2 to the m, and is congruent to 2 mod m sub n. And it shows that, therefore, this implies that Mn is a pseudoprime to the base 2. To base. Now, as a corollary to this, we have actually, there are infinitely many pseudoprimes. Corollary. There are infinitely many any pseudo prime to the base 2. Okay, here's the proof. Remember we have shown that I'm going to put it n sub 0, which is 3421, is a pseudoprime to base 2. That m sub 0 is equal to 2n sub 0 minus 1. Now, remember that when n sub 0, when n, the previous again by the theorem, m sub 0 is a pseudoprime to base 2, is a pseudoprime to base 2. And of course, m sub 0 is bigger than n sub 0, the original one. Now we're going to let we use this notation in here. That m sub 1, n sub 1 is equal m sub 0. Then m sub 1, which is equal to the n sub 1 minus 1, is also a pseudoprime. That's the same theorem, okay? And in general, if we let n sub k equal to, let me see what notation I want to use in here. Yeah, actually m sub k, capital M. To the nk minus 1. Let me see here. All right, where k is equal to 0, 1, 2, so. So all of these actually is defined in terms of m sub k. So these are pseudoprimes to base 2. And moreover, they are actually strictly increasing, means we have an m sub 0 to the first one is less than m sub 1, less than m sub 2, and so on. And since there are infinitely many k's, there are infinitely many pseudoprimes, of course. All right. Now we need to come to those pseudoprimes that are pseudoprimes to every base, to every positive integer as a base. Actually, the congruence, Fermat congruence holds. Such numbers, we call them Carmichael numbers, or we call them absolute pseudoprimes. So I want to define this. In other words, we might ask, are there composite numbers or pseudoprimes to every base? Are there pseudoprimes to every base? B bigger than. The answer is yes. Such pseudoprimes are called absolute pseudoprime or Carmichael numbers. Again, they are discovered by Robert Carmichael, (1912). He conjectured that there are infinitely many such numbers. Such numbers, and gave an example of such a number. This number, which is n equal 561. So this is the smallest, in fact, Carmichael number. The proof of the conjecture, this was proved in 1994 by Carl. Let me see how we write the name correctly here. Pomerance. And others. These are mathematicians at the University of Georgia. All right. So let's actually officially define what a Carmichael number is. And then we're going to give an example and study a couple of properties of Carmichael numbers, and that would be it. So here's the definition. A composite integer n is called a Carmichael number or an absolute pseudoprime if for every integer b bigger than 1, b to the n minus 1 is congruent to 1 mod n, where we see in here mod n, okay, okay, for every n. Let me write actually in here with greatest common divisor Pn equal 1, then this congruence holds. All right? And let's look at actually an example of a Carmichael number, the smallest Carmichael number. And then once we prove some theorems, we actually could generate many more. So here is an example. N equal 561 is the Carmichael number. First of all, we have 561 is a product of a 3, 11, and 17. In fact, it's a theorem which says that any Carmichael number is the product of at least 3 distinct primes. In fact, we're going to show that a Carmichael number cannot have a repeated prime in its factorization. It's square 3, what we call it. All right? So we're going to let, again, b bigger than 1 be an integer, such that greatest common divisor of b and 561 is equal to 1. This would imply because the greatest common divisor of b and 561 is equal to 1, so the greatest common divisor of b and any of its factors is equal 11, all equal 1. B and 17, all is equal to 1. So you can apply by Fermat theorem. We can say that b squared is congruent to 1 mod 3. And the same is true for all others. Let's go with this, and also with this one, we can say that b to the 10 is congruent to 1 mod 11. And b to the 16 is congruent to 1 mod 17. All right, now we're going to build the B560. And we can write this as b squared to the exponent 280. But since b squared is congruent to 1, so this is congruent 1 to the 280, which is congruent to 1 mod 3. Similarly, the b to the 560 is b to the 10, 56. And again, we have this is congruent to 1 mod 11. And finally, the 16 becomes b to the 560 is equal b to the 16 to the power 35. And again, this is congruent to 1 mod 17. Now we can multiply all these together, then we obtain that b to the 560 is congruent to 1 mod their product. 3 times 11 times 7. And it shows that 561 is a Carmichael number. All right. Next, I want to prove a couple properties. Carmichael numbers. The first one, it says that a Carmichael number is a square free. Meaning it does not have any square in its factorization. Or to be more specific, does not have any prime. All right, appears, it means all its primes are distinct. Okay, so let me prove this. So this is a remark. A Carmichael number, a Carmichael number is square free. What does this mean? That is the prime factors of any Carmichael number are distinct. Because they cannot appear to the third, because this means they are to the square. Okay, so it means I don't have any squares. All right. All right. So let's actually assume that to prove this. Assume that n is a Carmichael number. So this implies, and let's assume that actually A is an integer that is bigger than 1, right? And greatest common divisor of A and N is equal 1. Then, because it's a Carmichael number, we have this actually congruence actually 1. Actually, let me make this. I don't need this. I'll just make it actually congruent. I'll need this. Okay, so let's take this one. Mod 1. We're going to do this is by contradiction. So we're going to assume that P is a prime factor of N, and P squared divides N, means it actually the prime appears at least twice in the prime factorization of N. All right? Then we're gonna take A to be actually equal to this P. Then we have P to the N is congruent to P mod N. And also this implies that P to the N is congruent to P mod any divisor of N, for example, P squared. So this is a property for congruences we proved earlier. Now let's see what we have in here. So we have p to the n is congruent to p mod n, and p to the n is congruent to p mod p squared. All right? You're gonna see there is a contradiction. You also have p squared is, of course, divides p to the n. All right? So this implies that p to the n is congruent to 0 mod p squared. All right, so we have altogether now, this implies that p to the n is congruent to 0. All right, and also p to the n is congruent to p mod p squared. Well, this last congruence implies that p squared divides p. And this means p is a multiple of p squared, but this is, of course, is not possible. This is a contradiction. So the only thing which, we have committed in here is this p squared is actually a factor. So of n, so it cannot happen. The last theorem I want to prove is give us actually a necessary condition for a number to be a Carmichael number. Actually, it is a sufficient condition. Sorry, it's if something is okay, let me write it down. It's a sufficient condition. 5.3. Let n be a composite. Square free. Not have any primes repeating. Square free integer. Let's say that n is the product of these distinct products. Where Pi does not equal Pj for every I does not equal j in 1 and R prime. Then if Pi minus 1 divides n minus 1 for every I, then n is a Carmichael number. So this is actually a sufficient condition. All right. Well, let's go through the proof of this. And actually, it's not that hard. First of all, let's take a positive integer such that greatest common divisor a and n is equal to 1. And this implies that, of course, a and any of the prime factors of n is relatively prime for every I between 1 and r. Now we're going to apply Fermat's theorem to each one of these primes. by Fermat's theorem, we have A to the power Pi minus 1 is congruent to 1 mod Pi. And this is for every I. All right. Now, since the PIs are actually we have this condition, since Pi minus 1 divides n minus 1, this implies n minus 1 is equal T sub I times Pi minus 1 for some Pi in Z. All right, well, let's look at the we know that n is composite. All I have to do is to show that actually a to the n satisfy Fermat's condition, so n minus 1. So this is equal to actually a to the Ti times Pi minus 1. And this is true for every I. All right, but remember that this one is congruent to A, B, I minus 1. We could write this one to the Ti, actually equal, fair. And now we have all of these are congruent to 1. So this one is congruent to 1 mod Pi, all right, mod Pi for every I between 1 and R. Then since each one of them is congruent to 1, then A to the n minus 1 is congruent to 1 mod their product. We use this idea many times today. And this is, of course, mod, which implies A to the n minus 1 is congruent to 1 mod n. And this implies n is a Carmichael number. No. All right, so this takes care of the proof. In fact, a few examples of numbers that satisfy this. Let me just give one example in here, which you can check. It satisfies the conditions of the theorem. Let's say these are very rare, the Carmichael numbers. So this is 7 times 23 times 41. Which you can check if actually they satisfy the divisibility of each prime minus 1 is divisible by n minus 1. Okay? And that will be it. All right? We'll stop right here.